Hi everyone. Yep, so my name is Jay, and today I'm here to present some of the work that we've been working on in Daft. We actually gave a presentation last year at PyData Global 2022 when Daft was just a few months old. So I'm really excited to show everyone, what we've been working on and some of the recent updates and how kind of the whole vision of the Daft data frame is really, really coming together. Um, During this session, I'll be doing a bunch of demos, which will take a little bit of time to run, sometimes between a minute or two. So feel free to drop your questions in the chat, and we can actually jump into those questions as we go through the demos whenever we have time in between. So let's get started. Just a little bit about me. So yeah, I'm a co-founder at a company called Eventual. We're the ones maintaining Daft. Prior to this, I've worked in biotech and autonomous driving, mostly working on distributed data systems, building these data systems for machine learning workloads, dealing a lot with cloud infrastructure, a lot with distributed data infrastructure, etc. And now I'm a core maintainer of Daft, and you can find us at www.getdaft.io. So first, what is Daft? I find it easier to show rather than tell. So I'm going to go ahead and share a notebook where it might be easier to just get a feel for what Daft is just by looking at the notebook. So first of all, Daft is a Python library. You can easily install Daft with pip, where you do pip install get Daft, and you'll get all of our prepackaged wheels from PyPy. Daft is a cloud-native data frame API, right? So if you're familiar with libraries such as PySpark, Polars, Pandas, Dask, these libraries all have kind of a data frame API. Very similarly, in Daft, you can load data frames from various data sources, and when you show the data frame, this is what a data frame looks like. It has rows and it has columns. In this case, there's three columns: the path, the size, and numRows column. Each column has a type, right? UTF-8, int, 64, and then this is the data within that column, right? And so Daft allows you to load from a bunch of different sources. It's very cloud native. It even allows you to do things. In this case, I'm actually globbing a cloud path and returning a data frame of all the files from within that path, right? And then, obviously we also support reading CSVs, Parquets, JSONs, and reading, thousands of these files at a single time, just through these simple APIs. And you just have to give it kind of this S3 prefix to say, hey, I'm trying to hit this S3 source in the cloud. And yep, so Daft is a data frame. We have all the other data frame operations that we've all come to expect, like join two tables together, sort the data frame, create a new column using transformations of previous columns, filter a data frame, etc. And Daft also supports a full kind of cost-based query optimizer to optimize your queries before actually executing. So that's all fine and good, right? But what makes Daft special? There's a whole bunch of data frame libraries out there. Why did we try to build Daft? And what is the special sauce? And so Daft is really good at what we call complex data types. So these are things such as URLs and images and tensors, and these are types in Daft that are defined on our data frame. But when you define the operations in Python, so like this, you say, perform a URL download on the path column, and then perform an image decode on the new data column. And Daft will then actually run everything in Rust, which makes it really, really fast. We use a lot of cool async Rust and bind it to Python to make this work. But yeah, so you'll notice here that Daft has native types for bytes columns. It's called this data column is type binary, and then we have also native types for image columns. In this case, these are the images that we've downloaded from these URLs. And so it's really easy to go from URLs like binary data to images to resize images to tensors. All these data processing tools are kind of built into Daft for you and run really, really efficiently. And last of all, Daft is distributed, meaning that we support execution both on a local Python multi-threaded backend, which is what I'm using right now. This is running on my laptop. Or if you need to use a cluster of machines, you can connect it to a array cluster. It's very simple to do that. You just kind of call this Daft context set run array. Then now all of a sudden your Daft data frame with the same syntax has access to 1,000 cores and terabytes of memory if you run stuff in the cloud. So that's kind of a brief introduction to Daft and some of the motivations behind why we wanted to build Daft and saw this gap in the ecosystem for distributed data frames that were really, really good at this type of data processing. Yeah, and today's so what's new since last year, right? So since last year, we've built in a lot of our Rust core internals in Daft. We've seen a tremendous speed ups in Daft execution through that. We've built a lot of native types like images and tensors and embeddings, URLs, and operations on those types. We've also been running a lot of benchmarks. You can check out our blog to see how fast we run on 1 terabyte worth of very typical database TPCH benchmark. And today's talk, we're going to talk about how Daft has really, really built on its I/O layer to pull data very, very efficiently from S3 and the cloud in general. And so to motivate the talk, why do we care about cloud I/O performance in the first place, right? I'd argue that it's probably the most important thing when we're talking about performance of data frame libraries in the real world, because oftentimes the data doesn't just sit on your machine, the data sits somewhere in the cloud, right? So this is kind of the setup usually for a real world scenario of querying data. You have object storage, something like AWS S3, which we will be using in our demos today, and you have your query engine. This can be pandas, polars, Daft, PySpark, and any query engine. Really, the query engine might be distributed, meaning that it's installed across multiple nodes and machines. And now the first thing you have to do when you run any query, right, is you need to pull down data from object storage. That's like fundamental. You need to grab the data, pull it down to your machines, right? And then the second thing that's really, really expensive in these query engines is inter-node communication, right? Because the nodes need to shuffle data amongst each other. For today's talk, we'll focus on the first part, which is how do we download and deserialize as little data as fast as possible from object storage, right? And how can we make this super, super efficient so that in the first place, we can get data down so that the query engine can then work on it. And how do we measure what is considered good performance? So for the demos today, I'll be running Daft on the local PyRunner. On the R5 8x large machine type, it has these characteristics. The network performance advertised by AWS is 10 gigabits per second. And so if we can hit that 10 gigabits per second, then we know that we're being really efficient with all the network bandwidth that's being provided to us. This machine is fairly large. It has 32 cores and 256 gigabytes of memory. But we'll also see that we're able to process very, very large data sets, even with this setup. And yeah, so without further ado, one last thing, just to help people orientate around all the tools that we're using, I'm going to be using a tool called IFTop, which when you run it, it will tell you information such as the total amount of data received since the start of IFTop, the peak amount of data, the peak bandwidth that was running since the start of IFTop, and also the average receiving bandwidth over the last 2, 10, and 40 seconds. And so I'll be referring to these numbers quite a bit as we go through the demo, because we'll be able to see how much data is actually flowing through the network on that machine. Cool. So now that we've got through all the kind of boring pieces, let's go straight to the demos. I'm going to be running Daft in real time, and I'll share the other screen. All right. So yeah, this notebook right now is actually running in on an EC2 instance. So I'm gonna restart IFTop. At the bottom here, we'll see the IFTop instance running. Oh, I don't know if, let's see, I can't drag my face away. So let me make this screen smaller so that we can all see the bottom. Whoops. Can I drag it to the side? It's okay. Well, I guess we'll try to take a look at the peak usage instead of the running usage because I can't seem to get my face out of the bottom right of this screen share. Let me try one more thing. Move it to the side. Yeah, that's unfortunate. But I think we'll try and look at the peak memory utilization instead, which oftentimes isn't as accurate, but we'll see. So first of all, I'm going to use Daft now to just read a bunch of Parquet files. This is about 22 gigabytes worth of Parquet files, which is about 44 gigabytes when decompressed in memory. And so when I run Daft and I start reading data, we'll see that in this case, actually, you can't really see it on this screen share, but IFTop is also overflowing for some reason, but it peaks at about 9 gigabits per second, which is really, really good, right? Because, thank you. The screen share works now. So you can see that it peaks at about 9 gigabits per second. And this query will complete in about 30 seconds. Oh, whoops. Let me restart this kernel. I think the kernel crashed. And I'll restart IFTop as well. And yeah, so Daft is able to really make use of the network bandwidth here super efficiently. It's pulling data down at about 9 gigabits per second. This is a very simple query. It's just grab all the Parquet files, put it into a Daft data frame, right? And so we expect it to be able to parallelize in S3 super efficiently. Now we can try, what if we only wanted 2 columns from our data frame, right? Daft does perform a whole bunch of very interesting optimizations here. Without optimizations, you'll see that Daft will attempt to run a projection on top of the scan. But then if we run optimizations, Daft will understand that, hey, this projection, actually, I can just read 2 columns from the scan instead. So it will fold that projection into your scan operation. And now it will say, hey, projection pushdown, I only want to read 2 columns from these Parquet files, right? And so we'll see now when I run this that the network bandwidth goes up to about 5 gigabits per second. And it's very, very fast. This completed in 3 seconds, right? Pulling all that data down because it only needed 2 columns. And so Daft is able to use that from Parquet. Parquet is a columnar format and only grabs 2 columns, and it's able to pull down this data incredibly quickly from S3. The next thing I wanted to show you, which is I think super cool, is what if you didn't want specific columns? You wanted specific rows, right? And you give it this predicate, which is we're saying now, give me only rows where the L order key column has values less than 100, right? And so if you run this, Daft is actually able to do this very, very quickly. Naively, you would think that you would need to pull all the data down, run this predicate across all the rows just to get the rows. But because Parquet has a lot of interesting metadata about those rows, Daft can actually make use of that metadata to very intelligently prune out files even that it doesn't have to read. And so this query, where you would think you might need to pull down the entire data set of 22 gigabytes, Daft is able to do in 2.5 seconds, right? And this is reading from S3. And it's able to do this incredibly quickly, without having to pull the actual data down. This is what we call in Daft metadata execution. So the next thing I wanted to show is kind of very near and dear to my heart. I think I've been working on a bunch of problems relating to many small files in the cloud. Where let's say you have 10,000, 100,000 small files in the cloud. How does that perform there, right? So we've actually been running a lot of optimizations around this. The first thing is I'm not sure if people have tried this, but listing files in S3 is actually incredibly painful and expensive. I've seen this take minutes even on certain large data sets. Unfortunately, today I only can show you, I have 10,000 files sitting around, and so I can show that to you. The naive approach for listing these files will take about, let's see, 2.5 seconds, right? This is listing files using the Amazon Photo 3 library, which is, I've written this code at least 20 times in my career so far, where I'm just trying to list files. Let's see how fast Daft can do the same query, listing the files in the same bucket and same prefix using our from glob path method. It takes 300 milliseconds, right? And this is because we're very efficiently able to run these LS queries and parallelize them for hierarchical data sets, which is oftentimes the case where you might have your data in kind of a hierarchy of like year, month, and date. And Daft is very, very efficient with listing those files. In this case, it's listed about 10,000 files across in this data set in 300 milliseconds. And this really adds up because as you go up to 100,000, 200,000 files, right? The time taken to list files in a naive way will scale linearly. And Daft, this globbing mechanism that Daft has is actually integrated with everything else. If you're trying to read Parquet, CSV, and you pass it a glob, Daft is able to resolve those globs very, very quickly. So that's the first thing you have to deal with when you deal with small files. Just listing is expensive. The second thing is that can we read 10,000 small CSV files? And the answer is yes, we can. And one way that Daft does this is that this same bucket with 10,000 small CSV files, when you try to read it in Daft, it actually coalesces a lot of these files into one what we call micropartition. And we do this because we know that these files are small and we can kind of batch the reads to these files to make them incredibly efficient, right? So this is going to run for about a minute. And we'll see that the bandwidth usage goes up to about 2.5 gigabits per second, which is not great, but it's actually like already pretty good. And there are the dev team, we looked at this and we were laughing because there's actually a whole bunch of inefficiencies here. And I think we're actually bottlenecked here, not by bandwidth and by CPU. But the deserialization of CSVs is fairly expensive. And so this is something we're working on. But yeah, reading 10,000 files works flawlessly right now. We do a bunch of coalescing of the files. So while this is running, maybe I can answer one question from Martin. If you have faster I/O on S3 with Rust, S3, FS, GCS, FS would definitely be interested. Please contribute back. Yeah, would be interested in collaborating. The problem with the FS spec libraries is that they assume file system semantics over S3, right? Which is oftentimes not the best way of thinking about S3. There's a whole bunch of assumptions around read ahead, buffering, and stuff that doesn't really work well in a latency bound system like S3. And so we've actually custom built a lot of the things in Daft to be highly parallel reads, do a lot of like read planning up front to understand ranges and sizes of things that we need to read from S3. Cool. So let's move ahead with the demo again. We finished reading those 10,000 CSV files in about 1 minute. It peaked at about 2 gigabits per second, 2.5 gigabits per second. And the next thing I wanted to show you is, oftentimes when you deal with complex data, unstructured data, you might have a data frame full of like URLs pointing out to different sources, right? So one example could be a data frame like this, where I'm just reading a bunch of JPEG files, right? Give me a data frame full of paths to the JPEG files, and then I want to call URL download on those JPEG files. In this case, I have a magic number here. We're trying to figure out how to do this more intelligently. But when we run this URL download, we can see that like the rate goes up to, it should go up to about 9 gigabits per second. It's just maxing out this instance basically and reading these JPEG files super efficiently. There's about 40,000 files here, JPEG files, and it's going to be able to do this in about 20 seconds because we're maxing out kind of the bandwidth utilization on this machine. And there we go. This is about 13 gigabytes worth of data. If we were observing the total kind of memory that was flowing through, it was about 13 gigabytes. And we did this in about 20 seconds at a 9 gigabits per second throughput, which is really cool. This basically makes reading tons of small tiny JPEG files and tons of small tiny say NumPy arrays super efficient using Daft, and loading that into the data frame is incredibly efficient. And the last thing is If we weren't running a toy example, let's say we were running an actual query. This is TPCH query on a 1 TB data set. Question 1 of TPCH, which is a database benchmark. If you were running this, you'll see that Daft will peak at about, in this case, I believe this will take about 2 minutes to run, but it peaks at about 7.5 gigabits per second, which is very good. It's about 1 GB per second. On this machine. It's not quite saturating the machine, but that's also, it's a function of like how many cores are available on the machine and how hard Daft is pushing the resource utilization on this machine. You'll notice that this Q1 query is actually super IO bound. Most of the work is upfront in this like scan and then run a couple of things basically. Because yeah, the workload is IO bound. Once we're past scan, the workload completes incredibly fast. So I'm going to hop over to questions while this is running. Let's see. So Daniel's asking if AWS Wrangler is planned. Not currently, but if you join our Slack channel and have some suggestions on how we might be able to package something like that, we'd be interested in learning more. And yeah, so Shaul had a question. What is the window at the bottom? This was earlier in the talk, but this is a program I'm running called iftop. It shows you the rate of network throughput on this machine. And so we're looking at this row, which is the RX row, receiving. And then this is the peak memory utilization. Sorry, the peak network throughput in the receiving channels. Cool. So yeah, this should complete soon, but I'll just hop over to the main chat. Actually, let's just let it finish. It should be done just about soon. I think it usually completes in about 2 minutes. And yeah, so you'll see that once we're done with the scan, all these other things are just so incredibly fast, right? Basically, all the work that had to be done on this query was reading from S3. And once that was done, everything else was like, what was that, 5 seconds. So yeah, that's Daft, kind of some of the demos I had to show for Daft reading from S3. And let's go back to slides. So yeah, some final closing thoughts. Does it work at production scale? Yes, we've been working with Amazon. Daft is now reading petabytes worth of Parquet files daily at Amazon. Some initial results from them is that they've seen, up to 38% increase in their workload cost efficiency because the workload is fairly IO bound, just reading Parquet files from the cloud. Comparisons to other libraries, it's really hard to compare fairly, right? The data is different, the hardware is different, the networks are different. There was a really good talk at PyData NYC 2023, just a couple of weeks ago, benchmarking Spark, Dask, DuckDB, and Polars. Highly recommend you give that talk a watch. And just looking through that talk, I ran the TPCH Q1 benchmark because that's kind of what the talk dives into. Daft performs extremely well, given that we're using a much smaller virtual machine for this demo with less network bandwidth. But again, I think the data formats and size and file sizes are very different from what was used in the talk. And so it's not exactly comparable, but given that we're maxing out the bandwidth on the machine, I'm fairly confident that Daft is doing pretty well here. And yeah, the main thing we're working on right now at Daft is integrations with technologies like Apache Iceberg, Delta Lake, Hoodie, and Hive, which give us even more metadata on top of your files, right? It can tell us things like, oh, for this file, column X has values between 5 and 100. And so Daft at the planning level can actually do a lot of intelligent optimizations around figuring out which files we need to read, which parts of the file we need to read, and doing a lot of intelligent pruning there to make this even faster. And if you like what you see, come chat with us. We'd love to collaborate. My email address is actually down at the bottom there, so feel free to take that down. Yeah, that's all I have today, and happy to take any questions. Drop them in the chat. So if there aren't any questions, Daniel, actually, if you're still in chat, I'm curious to learn more about what you mean by a convenience package like AWS Wrangler. I'm not familiar with AWS Wrangler, so if you wanted to elaborate, that could be useful. Or just get in touch with me on my email. We also have a Slack channel that we use, a community Slack channel. So feel free to get in touch with me there. Thank you. Okay, so AWS Wrangler makes it much easier to read and write to Athena, for example, and it makes the whole AWS I/O to Pandas much easier. Yeah, I've actually found that like the PyArrow S3 file system is not bad. Daft is, depending on the workload, can be much faster than the PyArrow and I guess the Arrow C++ S3 reader. It's not bad. And so if you are trying to read I/O into Pandas, you can try using Daft, which is just Daft read and then you do .2 pandas. That could work. Or you can also just use the Pyro one, which is I think Pyro parquet dot read table, and you have to pass in like a file system object, and then you convert that into pandas. Yeah, but maybe I'm guessing AWS Wrangler probably wraps some of that to make it efficient. Yeah, just as a quick, I guess, clarification to the partnership we have with Amazon. They were previously using Pyro, and then they substituted Daft in. We were seeing, especially around much more aggressive column pruning reads, we were seeing Daft outperform Pyro by quite a bit here. So what features of Rust enable this? Yeah, so we are actually using a whole bunch of async Rust in Tokyo, which is an async Rust runtime, and so we're able to run kind of multi-threading, Rust multi-threading, not Python multi-threading, right? So we completely release the GIL at that point, which makes it very, very fast, and then we are able to run all of our operations in async Rust. On top of that, what we've built is also a fairly sophisticated planning layer around understanding specifically which parts of a file we need to read. We do a lot of intelligent batching of requests and retry policies with AWS S3 to make all this work. AWS S3 has a Rust SDK, which exposes a lot of the lower level kind of HTTP level parameters that we can use to very efficiently query data from S3 and apply some intelligent retry policies that can help us work very well with AWS. But we also expose all of these parameters in a config. And so if you have other S3 compatible storage like MinIO or I think Apache Ozone is another one, or even a Ceph cluster, you can actually tune these parameters so that the Daft can be well behaved when interacting with your S3 compatible storage. Regarding Microsoft Azure, we haven't optimized it for Microsoft Azure. It works with Microsoft Azure right now. We accept, I think, AZ :/ and ABFS : / URLs. But get in touch with us. We're keen to doing more optimizations there as well, given how Azure is, getting a lot of prominence in the ML AI space in general. Yeah. Get in touch with us. My email's there. Just drop me an email. I think we're at time, right? So, Donovan, feel free to take over.